All right. Okay. Well, welcome everyone to another episode of GPU Mode. Today, I'm really thrilled to have Yusheng Zheng, who's here to talk to us about like observability. I first became aware of their work, like basically looking at like different kinds of like profiler infrastructure. eBPF is something that's been very popular in the Linux community, but not as something I've seen necessarily a lot of like GPU centric people talk about. So please, without further ado, please welcome Yusheng.
Okay. Thank you, Mark, and good morning, everyone. I'm Yusheng Zheng, and I'm currently a PhD student in UC Santa Cruz, and I'm also maintaining a open source community about eBPF called Eunomia BPF, and I've been doing a lot of work in the eBPF space, and actually I just begin to look into the GPU in the past year, so I might not be so familiar with GPU, I'm just trying to combine the eBPF and GPU together to see how eBPF can help shape the GPU world. And so here is the agenda I'm going to talk about today. So the first thing is about background. Maybe you are more familiar with me. So it's about what's the GPU stack overview and the workload diversity of GPU space and the problem and why we need a eBPF. And what's the eBPF and how can we write the eBPF program? Then we will start to discuss our exploration, which is include device-side eBPF, which is we can offload eBPF to GPU kernel. We can do a lot of observability tools and props, and maybe we can also do some scheduling and prefetch things. Another thing is not just about observability, but also include extensibility. We are looking into where we can observe a lot of information from a GPU driver, and also we can change some algorithms and policies in a GPU driver, and we can combine both the driver side eBPF and the device side eBPF to do more powerful observability and policies. So the first thing is about background. Typically, as a GPU stack, GPU have my application have three different kind of stacks. The first is the user space application, typically include like VRM, PyTorch, and some kind of user space driver and runtime. The second part is like a GPU kernel driver, which could be GPU's OS component. This includes some like memory management and scheduling. The third part is the GPU device, which include like some framework in running the GPU and some hardware schedulings, and the GPU kernel is also running this layer. This also includes some hardware caches and HBM. So this is some figures I traced with our tools. We can see different kind of application has diverse resource and behaviors. Some of them are compute bound, some of them memory bound. For example, the face is a vector search engine, and we are also providing like llama.cpp prefill and decode and some like PyTorch DNA training. These figures represent their memory access patterns. So you can see they might require different policies for different patterns. And also, because HBM is very expensive and has limited size, some models often exist their VIM. For example, if you want to do MO inference or KB cache offload for inference, and sometimes large data sets for DNA training, you need to place your memory in place some of your model memory in GPU and place some of your memory on CPU. This is called memory offloading. And You might also want, like, if you are doing inference and training both on the same device, or you are doing multi-tenant inference, you need to schedule different application. And some of them are latency critical, some of them are like backend process, need high throughput. This create conflict memory complications and like different compute usage. So the problem here are mainly two sides. The first side is called invisible. A lot of GPU stack and GPU application are black box, like a runtime, like a CUDA runtime. They might be closed source. Their internal state is not exposed, and some of them are driver. So, uh, in a Linux kernel, you might want to understand why a driver in UVM want to view this page instead of another page. What's the access pattern of your device, and why your GPU's kernel is scheduled like this. Sometimes kubectl only give you like fixed events instead of allow you to program the event stream. Also, firmwares and device executions is also remain like firmware is completely closed source. So device execution you can only like do profiles through MVBit, and kubectl doesn't give you parallel WAP metrics from host. And also it's hard to correlate the CPU and GPU together. The second part is inflexible. A lot of GPU policies like driver UVM memory and driver scheduling, they are static policies. For example, UVM has only LRU evision and tree-based prefetch. The driver scheduler is round robin and fixed time slice. On your GPU device and GPU kernel, the thread scheduling is also fixed until you have like NVIDIA has introduced their new CRC features in Blackwell. You can do some fine-grained control after that. It's because of this invisible states and like closed source GPU stack. It's hard to change their behavior. Some people use LD preload to do changes before the GPU, the CUDA loads the GPU kernel into a driver. Some people try to modify the kernel driver, but it's hard to modify them safely. So if people want to do observability and extensibility, people typically has these approaches to do that. Some people are trying to do it in the user space runtimes, like inside their framework, VRM or SQLine. Some of them are doing it with user space LD preload themes. But these things are like application bound. You cannot do cross-tandem visibility. So you cannot it's hard to see through the entire system, like the OS behaviors and see if you have multiple applications, like multiple process running on your GPU at the same time, it's hard to see them as with one framework if they are in different frameworks. It's also hard to access low-level driver mechanisms inside their Linux kernel drivers. People already try to invent some more device profiles like MVB and kubectl and like other papers like Neutrino. MVB is a little bit higher overhead, and kubectl also limited the partial visibility. You cannot easily trace the different GPU threads like MVB did. It's also hard for them to do the cross-layer program. For example, you need to extract the kubectl information and correlate it with the CPU information to get what you want for a big picture. Other people might do like driver modifications to change their policies, but policies are these policies are typically hard-coded and hard to maintain deploy. It will also introduce some safety risks. Linux kernel has already provided some tracing tools in the past, but first GPU device mainly remains a black box. There are also limited programmable hooks in the GPU drivers for transient behaviors and for observability. So our insight is like, I think GPU needs observable and extensible OS interface. For observability, it's because the device execution space is invisible from host. You cannot see a lot of fine-grained information when you are doing policies, and existing providers are typically read-only or have high overhead or cost grain like Kubernetes. So you need a more fine-grained, low overhead and cross-layer observability tools. It might work like a dynamic binary instrumentation on your GPU kernel. The second part is like extensibility, because the policies are hard-coded and hard to change safely. And driver has the global cross-tandem visibility and hardware control, so we can do like safe and dynamic power cloud policy customization, like change the algorithm in GPU driver. So we can implement some like programmable hooks in GPU driver. People already do so with eBPF in GPU, like they are doing, like in CPU, they are doing CPU schedulings, like schedule expense. So the idea of GPU expense, part of the idea is like we create a programmable interface like people do for CPU scheduling.
Sorry, Yusheng, before we go for questions, do you mind just so on your screen, do you see the StreamYard is sharing your screen? Stop sharing, hide. Do you mind clicking on hide?
Okay, sorry.
No worries. Okay, so one question is on slide 4. Someone is asking, what was the y-axis?
So the y-axis is the address space. So you can see the addresses here. So it's like showing how memory access is changed when time is changed.
Oh, I see. Okay, got it.
So we can see different application has different access patterns.
Yeah, I don't think I've seen anyone show this. Like, this is kind of interesting. Like how prefill is sort of just like this like little short line that's like very nice and neat. And like a fast query is like kind of, yeah, it's very interesting. So this was like a custom profiler that you developed for these pictures?
Yes.
Oh, I see. Okay, my second question is like, do you mind going to the next slide maybe?
Okay.
One more. Ah, yes. So here, I'm wondering if you could like help people understand at a high level what are the differences between like NVBit, Neutrino, CupT. I think these show up a lot in the profiler community, but maybe people that don't work on profilers actively may not be aware of what these tools are. Do you mind just speaking more a bit about them?
Okay. So NVB is more like NVB and Neutrino are typically in the same kind. They are dynamic binary instrumentation tools. You can like when your CUDA kernel is logged into a runtime and before it starts running on your GPU device, the NVB and Neutrino can change your GPU kernel and like insert some of logic in it. So it can trace your thread behavior. It can trace your GPU threads and see some like fine-grained information. This is also how the BPF time and GPU extend works for the device side eBPF. The Kubernetes is more like a profile interface. NVIDIA has provided as their part of their CUDA tools. It's a standard interface which you can get some metrics. Metrics is like or some traits is like when the GPU kernel is executed on you, like some timestamps of the GPU kernel start running on your device and or is finished running, or like some driver events or runtime events. It's like a kind of event string.
And so the way like libraries then like because I mean tools like NCU are quite convenient because people don't need to change their code.
Yes.
So is the way that works, it's similar to like, is it like again like a user space LD preload, or do they use like different mechanisms to yeah, how do they insert hooks to be able to get the metrics on
Yes.
a kernel?
Typically NCU and like inside profile is a wrapper of the kubekey. They are based on kubekey, so it's like more convenient from end.
Okay, got it. Okay, we can keep going then. Thank you.
So if we so maybe I can continue through the slides.
Oh yes, of course. Sorry, I was just saying. Please continue. Yes, please.
Okay, thank you. So before we will start talking about what we did, I want to first introduce what's eBPF. eBPF is like safe and dynamic verified programs that are running inside the Linux kernel. So you can see there's a Linux kernel runtime and with a verifier and some kind of like helper and maps. You can run your eBPF program in your kernel and get a lot of information from your kernel for tracing and profiling and monitoring. You can also do like not just observability, you can also make it for networking and security and scheduling. So this kind of networking and security and scheduling does change your kernel behaviors, like block some process execution or change your CPU schedule algorithms and like do some packet filtering. And in your Linux kernel, it has a lot of projects for eBPF for all these kind of use cases. So eBPF program here is like some small C programs in my maybe a little similar to how CUDA kernel works. So it's also small C programs to expand the Linux kernel. It's compiled into a kind of called eBPF bytecode, and it can attach to some Linux kernel functions and some trace points like this. This is attached to a Linux kernel functions. It also includes some like helpers, which is Linux kernel API, and it can use maps to store information like or share key value states between user space and Linux kernel. The key idea of eBPF is that it has a verifier for guaranteed safety before execution. So with eBPF, you won't crash your kernels. There's no infinite loops and there's no illegal memory access. So it's like Linux kernel modules, but it's much more safe and much more restricted than Linux kernel modules. So it's a little similar to how the NVBIC and kubectl callbacks is like, but it's more like you write your own logics. You can dynamically attach without restarting, and it's more safer than this kind of NVBIC things. So our exploration.
Sorry to interrupt you, Yusheng. There are some confusions maybe in chat. Maybe let's just go over them. So I think like here did you see the screen by the way with the question?
Sorry, I cannot see your screen.
Oh, I see. So Sassy Nathan is asking, so can you compile eBPF code to run in CUDA? I think maybe the interop story wasn't clear to them.
Yes. So the core idea of GPU device eBPF is like we compile eBPF into PKX. So Yeah, so it can run as a GPU kernel, or like a GPU kernel, or as part of the GPU kernel.
Okay, this question, I'm not sure I fully understand it, but I'll read it anyways, which is, so someone's asking, kubectl is not JIT. Like, does eBPF allow us to dynamically allocate shared memory or optimal tiling, for instance?
Maybe I can I see the okay.
Yeah, and it's easier if you have, this one. It's easier
Oh.
if you do it on your phone or some separate device, usually on YouTube.
Okay, so
Yeah, I mean, I don't fully understand this question. I think it's probably like it's just that's not the intent of eBPF. Like, I feel fundamentally it shouldn't be to change the semantics of your CUDA program or to give performance sense. So maybe we can just maybe perhaps you please clarify your question and we'll get back to your question later. We can just continue with slides, I think.
okay, thank you. So I think eBPF here is not like dynamic allocation. It's like insert some of logic in your CUDA program for tracing here. So the first part of our device eBPF is like we want to do fine-grained profile. We want to trace per thread per WAF SM information, like how NVB this, but more safe and more safe because eBPFs can be verified and like more lightweight and fast. We can also bring like eBPF magic, so we can do cross-layer eBPF maps. Like we can easily correlate information between CPU and GPU. It can also do like dynamic instrumentation, so there's no recompile and restart requires. The second part is like we want to extend the linear GPU driver with eBPF. So we want to trace the driver level information, like some kind of UVM access patterns, some kind of like driver scheduling events, like how your GPU kernel is being scheduled on GPU. We can do like UVM programmable policies, like we can change the eviction prefetch algorithms. We can change the scheduling GPU TSG lifecycle scheduling algorithms. And also we can use standard eBPF verifiers for both device-side eBPF and driver-side eBPF. So what can GPU device-side eBPF do? We want to make it able to do fine-grained profiling, like we can get instruction level information, or like SM load balance trace, like this information. It can show how many threads has already been scheduled on which SM. So it's kind of like SM utilization histogram. So we can see different threads might have like hundreds of different thread counts being scheduled on them. You can also like provide information to help wholesale policies and do runtime adaptations, like change your kernel behavior on the fly. Another example is like launch latency. We want to combine the CPU side eBPF, which is the UProp things, and the GPU side eBPF, which is trigger and GPU thread entry with our BPF time runtime. So CPU side UProp is like we can attach a CUDA launch kernel, and GPU side is like attached at the it can show the like timestamps of GPU thread start execution. So the problem here is like kubectl only shows your GPU kernel can start it quickly, but it might be slow. You cannot direct get information from kubectl while your GPU kernel is slow. But sometimes actually the issue could be the thread blocks competing for SMs with other GPU kernel if you're running like multi-processing and multi-stream on your GPU at the same time. So there might be different kernels running on GPU at the same time. So kubectl cannot show like fine-grained thread schedule information. The kubectl can only see or with tools like NCO layer also rely on kubectl, so you can only see the GPU kernel start and end time for the GPU. But sometimes many blocks are waiting for SM results. But with BPF time, you can see like per thread web scheduling timestamps together with the CPU side launch time, so you can calculate their difference and see the exact problem. There's also like more tools like thread hits and kernel red snoops here. You can see each GPU thread, like how many the GPU thread count of being scheduled on the SMs, and like you can see the exact timestamps of your GPU kernel finish execution. So BPF time profile device side eBPF profile here is more like online profile instead of like on-site compute, which is the offline compiler. It has low runtime overhead and can provide per-thread trace, and it can also help you get cross CPU and GPU information. So it's also a little challenge to put eBPF on GPU. So the core challenge is like SMT has different execution behaviors. The original eBPF execution model assumes you are running on CPU, so they have less thread counts. You typically run eBPF as single threads. You have a lot of branch prediction, but on GPU, you are in the SMT, you are in the lockstep execution. This might incur like thread divergence and cause a lot of performance overhead. So the architecture of BPF time here is like the BPF time is working as a LD preload interface. You can compare the eBPF program source code with existing eBPF tool trends and into a eBPF user space application like BPF trace. So you can use the BPF time command to load your eBPF programs into shared memory, and then you can attach the BPF time LD preload library to a target process, and you can also use ptrace to do runtime injection, so it's not always requires LD preload. When you put this shared library into the target process, it can attach to the CUDA runtime and do the PTX injections, and then change your GPU kernel functions there. So the instrumentation process is like when you compile your CUDA application, you can get a fed bin, which includes your GPU kernel code. And then BPF time runtime will hook into these fed bins and decompile the PTX and get the original PTX of your CUDA kernel. And the BPF time runtime will also compile your eBPF program, which is eBPF bytecode, into the PTX and do the PTX injections. And so your the original CUDA kernel and the eBPF merge into the same PKS files. Then you load the PKS into the GPU device. So you can get information once the GPU kernel reaches the target point. So the PKS injection works like this. So you can dump the original kernel PKX and patch the PKX with some like inline hook style function call. And so when your CUDA kernel running into these instructions, they can jump into the eBPF program PKX, and then after the eBPF program finish running, you will jump back to the same location and continue execution. So you can do like props and read props or some certain trace points.
So Yucheng, I had two questions. If you could go
Yeah.
back maybe 2 slides ago.
Okay.
No,
This
maybe
one?
one more. Yeah. So
Okay.
the one with the fat bin. Sorry, the box diagram. One more. Oh no, sorry. One more to the future. Like maybe 15, I think. No,
Okay.
more.
This one?
No, one more. Sorry, yeah. One more. Okay, yes, this one. Where are you using NVCC here versus like so NVCC is like how you create the fat bin and then everything else is like your own custom code? Or do you still like need NVCC later once after you do the PTX injection? You still
Yes.
need to like
Yes. Once we finish the PKX injection, so it's like we get raw like PKX files. We need to assemble the PKX files into like SASS code. Here we need a VCC again.
I see. And then when you do PTX injection, is this primarily just you read the you read the PTX as a string and you inject code in it, or is like does NVIDIA provide tools for PTX injection, or was this your own tool to do this?
Currently, NVIDIA doesn't provide tools for PKX injection, so a naive approach is like just use like string replacement to
I see.
to give the PKX files.
Okay, and then but you're string replacing with a function, and so that function, PTX can just knows that like this is a foreign function, just call it. So the NVCC just takes care of the function being called
Yes.
later. Okay, got it. Okay, makes sense. Okay, wonderful. You can keep going.
So it's like here, so we can just insert a call here and then another call here. So there's not too much things to replace. There's also some trampolines to protect the function to avoid some like registered problems. So we can do some like, kind of like attach types. We can attach as the like GPU thread entry and GPU thread as we can do like attach as memory access, and we can also like try to create some like cluster launch control schedulers, but this one requires a lot of more modification to a GPU kernel, some hacks, and we can also introduce some kind of GPU specific eBPF maps like array and hash and ring buffers. You can also share this kind of GPU maps with your CPU maps. And you can also create some like GPU specific eBPF helpers. Sometimes you can also use standard user space eBPF helpers, but this incurs much higher cost. So these GPU maps and GPU helpers are also compiled into PKS and put as part of the trampoline. So compile as part of the GPU kernel. So we also need to do some optimization to make it like lower cost. The first one is like if you are doing partial eBPF, it might cost a lot of warp divergence and bandwidth waste. So we can execute eBPF once per warps instead of executing per thread, and like executing once per thread blocks. And you can have a verifier to check about them. If they are uniform, you can execute them per thread as well. This can reduce a lot of performance overhead. Another thing you need to take care of is the map placement. Um, because if you place the maps in the CPU memory as our original implementation, this will incur very high access latency. It's unacceptable. But sometimes you also need to access the memory from the CPU side, like pulling information and or sending information to CPU to make CPU access faster. So you need to have a map placement strategy. Some host-based access by GPU you can automatically place on GPU local memory. Sometimes core configuration you can place at host DIN. Some like bidirectional you can create duplicate versions and share between them. So because BPTime is running on the PTS layer instead of running on the SASS layer, and with our like optimization for the map placement and for the WAP uniform execution, BPTime can run with a lot of lower overhead than NVBit. So any more questions for this part?
No, this was very clear. I think we keep going.
Okay, thank you. So the second part is like expand Linux GPU driver with eBPF. So maybe we can go through two backgrounds here. The first part is like GPU task scheduling. So when a CUDA kernel is logged into your CUDA runtime and before it start running on your GPU device, you will first go through the abstraction called GPU channel is a command line queue for per GPU skins, and then the channel will be assigned to a TSG, which is test group, scheduling unit, and the GPU driver will create TSGs and communicate with the GPU's device, and then the third thing is like the firmware on your GPU device is managing the GPU kernel scheduling with the run list as a hardware schedule queue of TSGs. Run list might include multiple TSGs. Uh, because the GPU kernel launch typically bypass the GPU driver, the user space runtime, the CUDA library will write to push buffers and with doorbell registers, so you can only control TSGs in your GPU driver. So here is like a TSG lifecycle. You can control like time slice and interleave level, like priority and times. This parameter is not exposed at for user space, but we can use eBPF hooks to control them in GPU driver, which is I'm working on. Another thing is like unified memory. The unified virtual memory allows you to do the CPU offloading transparently and allows the unified memory part here allows the CPU and GPU share the same virtual address space, and it can assign the virtual address ranges with chunks, which is a physical block on your GPU driver. And when the UVM reach when your GPU, so the UVM works by migrating memory between the CPU and GPU. So if your GPU kernel execution encounters a memory, so it's on the CPU side instead of your GPU side, so you will trigger a page fault. So the UVM driver will pull the memory from the CPU side into GPU and pass the web execution and migrate memory and continue running the driver, the kernel. Because because the UVM here, like they are using black box policy, is very slow. So typically people want to manage memory themselves with CUDA APIs in frameworks. So we create some kind of BPF trace tools in GPU driver, like we can trace UVM memory life cycles and we can trace UVM prefect decisions. We can also trace like GPU scheduling events. By using the eBPF CPU tracing with some like GPU kernel tracing, either using BPF time or we can use kubectl. You can create a frame graph of. You can also create a frame graph like this, which includes CPU events and GPU events. You can show the which GPU kernel is triggered by what kind of CPU functions. So from beyond observability, we also want to change the GPU driver behavior. But a GPU driver here was not assigned to expose a programmable interface. So we want to make, if we want to make it more expressiveness, which means we need to expose low-level mechanisms, you will incur higher risk or higher driver safety risks. If we want to make it more safety, we will need to remove complex memory, UVM memory or scheduling decisions. So our approaches here is like we try to identify a narrow and safe interface so you can safely express your policies and while also keep it safe. It's like we create some kind of GPU block, like GPU block interface similar to a programmable cache model. Then you can use K-functions to move the GPU block from to head or to tail and create some policies for LFU, MIU, and FFU emissions and prefetches to like speed up your unified memory as UVM access. You can also create some like GPU kernel scheduling interface, which policy can set time slice and interleaf levels and access to reject some bindings, which you cannot do from user space libraries, and can help you ensure the multi-tenant fairness and isolation. We do some modification to the NVIDIA kernel to add these eBPF hooks. And so you can achieve a lot of performance improvements with the UVM, and it's even more faster than Llama CP's building offloading, and sometimes fast. And for both MOE offload and KV cache offload, a lot of maybe another problem is that hardware involve faster than software algorithm here, so you need to have a more extensible interface to do more prefetching, and C-based prefetch sometimes is not optimal for LLM and ML offloads workloads, and you can also ensure like when you are running multi-tenants on the same machine, you can also ensure better scheduling isolation and memory priority. Yeah, I think that's all. So we are also exploring because most of our tool here is working on NVIDIA stacks. We are also exploring to AIM and NVIDIA stacks. We have already created some proof of concept for SPF 5, but we need to do more runtime instrumentation to make it actually works better. Yeah.
Cool. Very cool. Thank you, Cheng. I guess I'm curious to ask you because in Unomia.dev you have so many different eBPF based projects. Which ones do you think would you be most interested in people contributing to or being users of? What would you hope the community do with your tools?
Yeah, I think currently most useful tools will be the BPF time tools. Yeah. Let me see which the so the GPU driver side. Okay, sorry. So the GPU driver is more like experimental things. So we have maintained the BPF 10 as a user space runtime for a few years, and so you can easily use it with a few commands and it's compatible with original eBPF.
Mm-hmm. All right. Well, very cool. Thank you, Cheng, and thank you so much for coming. I think we had some people in chat that were asking if you could share slides. So if you have time later, maybe just send them over to me. And it was a pleasure having you. Thank you so much for coming.
Thank you. See you.
Thank you, Cheng.